today is Sagnik from University of Birmingham. It's possible to. Thanks. Thanks for the invite and thanks for organizing this. I'm going to talk about recent algorithm design trend. I'm calling it the unified algorithm design. And this is going to be sort of like a survey. It's going to cover a bunch of papers with consistent authors where Joachim, Tawe, Danupon, Young and Stratton, the last two are the PhD student of mine. And all right, so let's get started. So some of you might have seen this talk given in ICAL this year. Danupon gives a version of this talk. So thanks to him for sharing some of the slides with me. And I'm going to assume n as a number of nodes, m as a number of edges throughout the talk. So we're going to talk about graph algorithms. And order tilde will hide polylog factors in n. Also in n, it doesn't really matter. Right, so let me start off with an open problem first. If by the end of the talk you solve this open problem, that's excellent. But if by the end of the talk you are interested in this open problem, that's good enough for me. So this is the open problem. So you are given an input, an unweighted directed graph. You don't get to see the graph. It's hidden, and you have a query access to this graph. What kind of query? So you have a cut query access. What do I mean by that? You can ask for a set of vertices, and it will tell you how many edges are going from one side of the set to the complement of that set. That's a cut query. It might seem a bit weird kind of query model, but I will try to motivate it throughout. And given two special vertices, S and T, source and sink, I want to know whether there is a path from S to T, or whether T is reachable from S. And in undirected graph, you can do it very quickly. You can just issue order tilde n many cut queries, and you will get it. Essentially, you're going to do some sort of BFS. If for directed graphs, where the reachability is more important, you can do it in order n squared. And it's not just for directed graph. The order n squared bound is not just for reachability. It's for a bunch of other problems. Essentially, what happens is like, if you look at this equation, it's like a cut of S plus cut of the complement of S. Because it's a directed graph, these two numbers are different. You can write it as a summation of the weights of the edges. If you look at the subtraction, then it's just like out degree minus in degree of a bunch of nodes. Yeah, that's the only thing that you need to figure out. So you can figure out the out degrees and in degrees and all possible WVs, the weights of the edges, by issuing order n square many queries. And that will give you a solution for a bunch of problems. So that can be solved. Now, to get anything better than n squared is an open question, and that's an interesting open question. And the conjecture essentially over here is that you can do it in n linear many cut queries. We are nowhere close to it, but I will expand more on this as I go along, and why this is interesting and what kind of impact it will have on other problems. Right, is the open problem clear? Now let's talk about unified algorithm design. So what is the motivation? So, when we talk about a problem in computer science, especially in our area, the measure of complexity is usually the unit cost in the unit cost run model, where you talk about runtime, right? But when you talk about the modern computation models, like distributed models, streaming model, NPC, PRAM, some of the things you have already seen, and also Christian will talk about streaming in the next talk. Each variant comes with its own measure of complexity. So let's see an example, maybe not an example, but what this models are doing. So in the streaming, the input is given in a way that you see those edges coming to you in a string, right? And your measure of complexity is like the local memory that you need to have in order to solve the problem, and a number of passes on the stream that you need to have in order to solve the problem. These are your measure of complexity. If you talk about distributed congest, the input is such that every vertex will know its neighborhood, and you need to solve some problem in a distributed way. The measure of complexity is number of rounds. Even in the local model that Peter mentioned, that's similar to this. In MPC, it's sort of like rounds. There are also many processes, and work happens in phases. So essentially, you optimize the number of phases. And in the query model, one of the simplest of all of them, essentially, you ask an oracle about some property of the graph, and you get that value, and you will be charged once, and essentially you are gonna minimize the number of queries to that. So these are many different models, and as an algorithm designer, this is a nightmare. So because you have the same problem, and you have to solve it in all of these different models separately, and this is not an ideal situation, right? So let's take an example like the minimum spanning tree, or the reachability problem, or the min cut problem. We know of good sequential algorithms or unit cost gram algorithms for them, right? So for minimum spanning tree, you can use Prim's algorithms. For reachability, you can use a BFS kind of algorithms, or min cut, you can use Kargar's algorithm. These are all well-known algorithms, but they are optimizing runtime. So when you have different computational models, these algorithms might not be optimal for that. So you can essentially the way the research works is like you come up with different algorithms. So essentially you fill up every cell of this matrix by investing, your research time and doing algorithm design specific to that model. Some might say this is essential, right? Because each model has its own unique constraint that we need to optimize. But if you look at it, if you look at the different algorithms, and if you work on it for a while, you get the feeling that you are solving the same constraint, but you're solving it differently in every model. Is there a way to unify that? So this is what I wanted to talk about. So can there be a cross-paradigm algorithm? I mean, this cross-paradigm is some name that we came up with. It is also can be called as a universal algorithm or a model agnostic algorithm. It's not a set in stone name, right? So this picture actually explains what I'm trying to mean. Think of cross-paradigm algorithm as an instruction manual. Every model comes with its own tool set, but using that tool set, you are gonna follow this instruction manual. So maybe if you have a Swiss knife, so you're gonna do some really hard work to do that instruction, but it is nonetheless that instruction that you're following. You might argue that why that should be true for any problem isn't it the idea of having such an algorithm, is it too good to be true? And that's the right question, essentially, why that should be the case. And what I'm trying to do in this talk is to give you some examples on some very fundamental problems for which such an algorithm is possible. And I feel that if you study a problem from multiple computation model, the lens is a multiple computation model, you will know more about the hardness of the problem than if you try to do it from one specific computation models. And I will say more about it very soon. Sorry about that. Okay, let me give you an easy example now. Minimum spanning tree. This is one of the most fundamental problems in graph theory, right? You want to come up with a spanning tree, and amongst all the spanning trees, this is the minimum cost, minimum weight spanning tree. And we know of many algorithms to do this. We know Kruskal's, Prim's, and there is also Borufka's algorithm. Now, amongst them, let's just focus on Borufka's algorithm. It's an algorithm which works with this instruction manual. So what you do is that you pick a node V and you find the minimum weight edge incident on it for every node V. Once you have done that, you contract those things and you have super nodes and you keep on doing it. So this needs only log n repetition of it. Why? Because in the worst possible case, what will happen is you find a node and it gets matched. By matched, I mean it found a min weight edge and it matches to another vertex, and this is the only two vertex which has got an edge in it, and this vertex doesn't have any edge to some other guy. So all in all, to say that if you do that in every iterations, you are cutting down the number of vertices by a constant factor. So you can only go on for log n many repetitions. Right. And now, this Borufka's algorithm is surprisingly versatile. If you look at the dynamic streaming literature, the best algorithm to find the MST is essentially an implementation of Borufka's algorithm. It uses some nice tricks called graph sketches, but nonetheless, that's the algorithm. In PRAM, in quantum, and all of them, the best possible algorithms is Borufka's algorithm. So I can think of it as an instruction manual. And how do you find that minimum edge is why you need the tool set from different models. Is the MST algorithm clear? If there is no such question, let me ask a few of my own. Borufka is log n factor slower than Prim's and Kruskal's because you are doing in this log n rounds, right? So that multiplicative log n factor is there, where Prim's doesn't have that. Well, there is more to worry in life than log n factors. That's my essentially the answer. You don't care. We don't really care about log n factors, so we are happy with Borufka. And even if you look at the best MST algorithm, which is linear, it uses Borufka as a subroutine. This is sort of the versatility of Borufka. But the more pertinent question is like, is it the only example? And my answer to that is no. You can find some other cool examples which follows the same kind of instruction manual. So let's look at some of the natural extensions for connectivity. So you can introduce edge directions to a graph, and now you can ask about reachability and connectivity, right? Whether S can reach T, or what are the strongly connected components in the graph. Or you can give weights on the edges, think of the length of the edges. And you can talk about single source shortest paths, like shortest path between two vertices, or from a source to all of the vertices. Or you can go a little bit farther and you can say that I'm not happy with just connectivity. I want to know how well connected the graph is, which means that you want to find the minimum cut of the graph. Right? These are all natural extensions. And not only that, these are all very fundamental to the point that they are taught in the graduate courses, even undergraduate courses. It's an undergraduate group, right? So you can see the strongly connected component, MST, single source shortest path, min cut algorithm, these are all there. These are very classic problems. And the state of the art is order m time algorithm for reachability, which is essentially a BFS. For single source shortest path, you do Dijkstra and you get m plus n log n. And for min cut, this algorithm in this book gives you an n square log square n algorithm. And they have got a bunch of follow-up and prior works on it. For example, Karger's Stock 96 paper gives an m log cube n algorithm, which is qualitatively better than n square log square n. because m can be at most n squared. If m is much smaller than n squared, then this algorithm wins hands down, right? And if you're following news from SOLA 2024, you will see that there is also a deterministic version of this algorithm available, which is linear runtime. So those are there. Now, if I ask you the question, one of these problems can be solved in multiple computation models in an optimal way, what would be your guess? Which algorithm is it? Any guesses? All right, so I mean, it's sort of like obvious with the amount of text I put in over there. It's the min-cut algorithm. So
can I just check? It's unweighted, right?
the min-cut is weighted. Yeah, you can
The
put
deterministic linear from SOLA 24, is it weighted?
Yeah. So the dynamic stream and congest and PRM, these are like three models that I listed over here. And everywhere over here, I mean, this is like a bunch of papers we had for the last few years, where you can solve it in almost optimally by following the same instruction manual. And I'm going to talk about what that instruction manual is very soon. But for reachability and single source shortest paths, these are outstandingly open questions, whether you can do it. Right, so let's start with minimum cut. So I'm going to make a quick detour to a puzzle. It's going to be a very nice puzzle. If you've already seen this kind of talks, you know the answer, essentially. So this is the puzzle. You have a matrix, n cross n matrix. It's hidden to you. You don't get to see it, but you have the guarantee that the matrix is monotone. In the following sense, if you look at each column, if you look at the minimum entry in each column, which is orange over here, and when you go from left to right, these column minimums will never move up. It will only go down or stay at the same level, right? So this, if you just trace these minimums, they form a staircase. This is one such example. And now what you have query access to this matrix. You can ask for IGN entry, and I will give you that, and you will be charged once. You want to find the minimum entry of this matrix, which means that it's the minimum amongst these orange entries. How many queries do you need? I will give you a few seconds to think about it. All right. One of the naive algorithm is like read everything, right? That's n squared. Can you do anything better than n squared? Well, it turns out that you can, right? You can do a divide and conquer. You can look at the middle column, read everything from there. Find the minimum entry over there. And once you have found the minimum entry, the search space is reduced to this area and this area. So any recurrence, right? So in n log n queries, you can do it. I mean, by the way, there is an order n query solution to this. And that's not useful for our purpose. This is the divide and conquer solution, which is going to be useful. So how do we connect this puzzle to min-cut? So,
Yeah, could you go back? I think I missed something in the problem definition. Go back to the. Oh, you can ask for an entry at a time. Okay, sorry, yeah, misread.
yeah, so to ask for this column, you already incur n, but you're only going to do it log n. So recall the min-cut problem is essentially trying to remove edges from the graph in order to disconnect the graph, right? So this is where the David Karger's breakthrough insight comes in. He said that in order to solve min-cut, you can essentially reduce the problem to this following problem. You are given a spanning tree of the graph, and you need to find the minimum cut such that it cuts at most 2 edges of the tree. So what's going on over here? If you have to search for min cut, there are 2 to the power n cuts through which I have to go through, right? With this, how many edges are there in a tree? N edges. So how many cuts are there that can cut 2 edges from the tree? Around n squared. So from exponential to n squared immediately, right? That's the search space. So I'm not going to talk about how this reduction works, but essentially it's amounts to repeatedly finding minimum spanning trees of the graph. And because we have seen MST is cross paradigm, this part is also cross paradigm. So let's just assume that you can do it in an instruction manual way. Now, there are n square candidate cuts, so we can sort of like put it in this matrix format, right? So the rows and the columns both are indexed by the edges of the tree. And you put in the value of the cut of the original graph that cuts these 2 edges of the tree. That's how you populate this matrix. Now, it is efficient to in streaming, sometimes it is efficient to compute n entries of this. But even then, if it is monotone, you only need log n passes, right? So the question is like whether this matrix is monotone. As it turns out, it's not. It is not monotone. It is far from monotone, actually. But you can do something about it. So this is something we observed, that if I take 2 parts of this tree and I put this matrix where on the left hand side I put the rows are indexed by the edges of path number 1, which is the blue path, and the columns are indexed by the edges of the path number 2, that's the green path. This matrix is monotone. And I might skip the proof of it. You have to, it's not very hard, essentially. But that's clear observation that we made, a concrete observation. And now, if I have this, you can make some progress. You can do a path decomposition of this tree. It can be a heavy line decomposition or a bow decomposition, centroid decomposition, any kind of decomposition that maintains some property. I'm not going to say which property it is, but there are many decompositions possible. And once you decompose the spanning tree into parts, you essentially pair those parts up and you solve the monotone matrix thingy on those pairs. Now, how do you pair those parts up? That's also requires some kind of cleverness. But in the end, you can do it in an instruction manual way. Note that whatever I said so far, this step requires MST, which is instruction manual type. And the monotone matrix thing that I mentioned is also a divide and conquer algorithm, and essentially it amounts to querying stuff, and that's also can be implemented in all possible modules. So this is essentially the algorithm. Decompose the tree into parts. Now, this is the second instruction, which I haven't explained. This is how you pair up those parts. And the third is like you do the matrix min entry on those pairs. Now, decomposing T into these parts can be done you need these graph sketchings, but it can be done in ordering internal spaces. Step 2 can also be done with cut sparsifier or some textbook kind of streaming algorithms, let's say Mr. Grease kind of algorithms. And the third one can also be done in log n buses because essentially they're inherently parallel, right? There are only log n steps of it. I'm being very hand-wavy over here, but the moral of the story is that all these steps can be implemented. Right. So when we did this work, our intention was not to improve the sequential runtime. But this is what I was mentioning previously. When you look at a problem from different models, you get to discover something which is the inherent hardness of the problem. And that might in turn give you some advantage in progressing even in the sequential model as well. As we have seen over here, from m log cube n, we get m log square n. Very modest progress, but a progress nonetheless when things are so close to linear. Right, is this clear up to this point? What minimum cut, why this is an instruction manual kind of algorithm? This is not just specific to minimum cut or MST. And the recent work has been, there have been loads of examples on it. For example, for negative way shortest path, for Steiner forest, for vertex connectivity, approximate max flow, approximate shortest path. These days, we are seeing algorithms where people are implementing a strategy which can be simulated in many models simultaneously. I want to say one caveat for this first point. This is, first of all, based on the Fox 2022 best paper, but this is only the reduction, which is cross paradigm. So the reduction from negative way shortest path to non-negative way shortest path, but once you go there, how do you solve the non-negative way shortest path really now depends on which model you are working on. And it's a very nice open question if we can unite those, that algorithm as well. At this point, we don't know how to do it. Right. And also you will see some of the results over here is written in preparation, in progress, and so on and so forth. Again, these are, as I said, like hot from the press, essentially. And now an outstanding open question, in my opinion, over here is to solve max flow. And why I'm mentioning communication complexity suddenly over here, because in all the models, in most of the models that we consider over here, even though historically the algorithm is developed in a siloed fashion, like there are techniques that is being developed in one model and that's not getting used so much on the other model. When you talk about lower bounds, the lower bound situation is very homogeneous. In the following sense, all the lower bounds is following from one model of computation called communication complexity. So it's essential to actually look at max flow, one of the hardest problem in this area, and to see what's the communication complexity of this problem. That will give you some headway towards a real hardness of this problem. We can do n square root n. There are some stars over here. This is not written down at this point, but a conjecture would be order n communication complexity for max flow. So far, so good? Now, the rest of the time, I'm going to talk about why cross-paradigm algorithm should exist for some problems, right? And my short answer to this is, I don't know. Thank you very much for attending this talk. I'm sorry. I'm gonna make some cases over here, essentially. So my case over here is that cross-paradigm algorithms works because these algorithms actually work in a weaker model. And let me try to formalize what do I mean by that. So let's fantasize about some kind of dream universal model, you know? If we can solve in that universal model any problem over here, you just implement in that universal model, and then once you have that universal model algorithm, you can just simulate in other models in a black box fashion. Now, I mean, think of this like an interface, an abstraction, right? We don't quite have such a very general trained universal model, but we have something very close to it. And I'm going to talk about two of them this talk. One is called dynamic query, which is something that I with my co-authors are working on, and something called minor aggregation, which I have no part in that research. This is done by some other people, some other group, but nonetheless, this is also a progress in that direction. So let's start with dynamic query. What do I mean by that? And again, things are very preliminary at this point, work in progress. So be kind. So now I'm going to talk about why I mentioned about cut query at the very beginning. And I'm trying to motivate that cut query right now. And this dynamic query is essentially a dynamic form of cut query. So for that, I need a very quick introduction to something called submodular functions. So, I mean, many of you have already seen what is a modular function. This is just going to be a recap of it. So submodular functions are set functions. Think of it, there is a ground of food items, and a set function is essentially cost of buying a bunch of those food items. Essentially, it's a function which is defined on all subsets of the ground set. And that set function is called submodular if it shows something called diminishing marginal gain. I usually motivate it in US style McDonald's function. If you have fries or chips, getting a drinks with it will cost you money. But if you already have chips and drinks, getting a refill is free. So essentially, if you have more, getting something included in it is going to be cheaper. So this is called diminishing marginal gain, and this is the usual formulation of it. Why this is important, why such a function is important, here is a real life situation. So let's say you have a room and you want to put sensor for fire, right? And I'm looking at how much information can you gain by putting an extra sensor, right? If you have too few sensors to begin with, putting a sensor now will give you more information about the fire than the situation where you already have a bunch of sensors. Then putting another sensor is not going to give you as much bang for bucks as the other case, right? It shows diminishing marginal gain. So that's a classical example of submodular function. And how that relates to graph functions? Well, if you look at graph cuts, it's a submodular function. So this is essentially the characterization of submodular function. You have two sets A and B. If you look at the cuts of A and cuts of B, and on the right hand side you look at the cut of A intersection B and cut of A union B, then you will see that on the left hand side this red edge is counted twice, on the right hand side it's not counted at all, right? So you can just count at this point and you see that the graph cuts is a submodular function. How do you solve a submodular function? Essentially, the way you solve a submodular function is you have access to submodular queries. You have access to queries like f of A or f of B for some set A. And that will immediately spatialize over here as cut query. You have access to cut functions, right? Does that make sense? Like why cut functions are important at this point? Now, suppose you have a cut query algorithm for solving something. And let's say I want to treat this algorithm as my instruction manual for other models. What's the problem? The problem here is like it's inefficient to even specify all the queries. Suppose you have n cut queries, right? How many bits do you need to specify this n cut queries? For each cut, you need n bits because you need to specify what cut it is and with answer to it. So n plus log n, so that's like order n. And if you have n many cut queries, that's already n squared amounts of information that you're providing. That's way too much information. Right? So here's an example. You have cut of S1 to SQ, and you need essentially n squared time and space to specify all these cuts. Now, dynamic cut query is somehow avoiding this blow up of information. What you are allowed to do is to make a cut query which is very close to what you have already queried. So suppose you queried S1, which is A, B set, the S2 is going to be one vertex different from S1. Or S3 is going to be one vertex different from S2 or whatever. I mean, to specify these cuts, you just need log n bits. So now if you have an n many queries required in a dynamic way, that means that you're not, it doesn't require too much information to solve the problem. Indeed, you can ask the question, that's a very big restriction on the kind of cut queries that I can do. Can I solve anything at all with this? Well, you can. For example, this is a paper we had in Stroke 2023, where we did not look at specifically cut queries, we looked at some sort of matroid queries called rank queries. And we showed that even if you look at the dynamic version of those rank queries, you can solve whatever you can already solve in the similar runtime. So it's not weaker. What about dynamic cut queries? Here is a conjecture, and this is the conjecture I mentioned in the very beginning. If you can show that reachability only need order n many dynamic cut queries in polylog n parallel round, then the consequences are amazing. You can solve congested click, streaming, everything in almost optimal way. And just this conjecture alone will improve a bunch of papers which are like published in the last, let's say, 5 or 10 years. These are all very like the top papers, the state of the art. Just one conjecture will do that. It's a hard problem to solve, all in all to say, which is why I put the question without a dynamic constraint attached to it. Even that we do not know. So that's a step-by-step process. You first solve it with cut queries, then you improve it to dynamic cut queries, and once you have it, you have all of this.
So you believe in this conjecture?
Yeah. I have no reason not to believe on this conjecture. And of course, it will break barrier for Maxwell and some modular function minimization. Like it's a side note over here, but these are concrete impacts that you have. That's a conjecture. What do we have? For min cut, whatever we said so far, is an algorithm which is a cut query algorithm. You can simulate it in the cut query. But you can ask the question, if I now put this restriction of dynamicness, can I solve anything? Well, this is again a work in progress where we showed that yes, not only you can do it exactly in the almost a similar complexity as if you didn't have the dynamic constraint. And again, because we have this thing, it has these consequences where so this alone recovers the results of 3 papers. So this is again a way, it's an instruction manual kind of algorithm. This is a true instruction manual. These are all just black box reduction at this point. Right, I have 5 more minutes. I'm going to talk a little bit about, well, I might skip this idea. I had a proof idea, but I'm going to talk about the last instruction manual work, which is called minor aggregation. So this is a technique that has been developed by Bernard Hauptler, Mohsen Ghaffari, Goran Žižić, and his co-authors. These 3 are constant authors of these papers. What does it say? It says, like, here is the meta model. In each round, you can design an algorithm which works in this way. You have this algorithm running in rounds, and in each round you can do these 3 things. 1, you can contract any subset of edges to create supernodes. 2, each supernode can send small messages to its neighboring supernodes. And 3, once this message passing is completed, you can compute some sort of aggregate function on a supernode. In the sense, it's like, think of the point of view of a supernode. It has got a bunch of messages from its neighbors, and once we have all these messages, it will apply some sort of aggregate function on it. What do I mean by aggregate function? Sum, max, or any commutative associative function, you know? Parity, whatever. If your algorithm follows this template, then, okay, so let me give an example where this kind of algorithm is like exemplified. Like Borovka, let's get back to Borovka. It's essentially these three steps that's happening. You are finding the mean weight edge, you're contracting them, and in the next step, when you get all the other means, you're essentially doing an aggregate, a mean computation on them to find the next step. Now, here's a result which shows that if you have a minor aggregation algorithm, so an algorithm which works in rounds, only does these three kind of things in each round, and it runs in polylog n rounds, then it will give you optimal parallel and congest algorithm, black box, right? So, okay, so that's a very nice thing to have. Can I have any algorithm, any problem that can be solved in this template? Yes, you can solve min cut, and you can solve approximate single source shortest path. Again, very basic problems, you can solve it in this way. And because you have these things, you have near optimal min cut. This is essentially they are recovering our result, but in a much more unified way. And you get PDAM algorithm as well on this. Right, so to summarize, cross-fired algorithm might look too good to be true, but there are a growing number of examples where this is essentially the way you solve problems. And this is also a useful approach to study problems. For example, this monotone matrix that I mentioned about min cut, the connection with min cut and monotone matrix would have remained undiscovered for quite a few years if we hadn't solved it in a cross-diagram way. There's no reason for anybody to connect min cut with this kind of matrix unless you see that that's the problem you need to solve in order to solve it in this model or that model or whatever. The open question is like, is there a better universal model? All this dynamic query, minor aggregation, they all work for a subset of models. It gives an instruction manual that can be implemented in a subset of models, but can we make it more general? Or on the concrete problem side, can we come up with a max-flow algorithm which makes order and dynamic cut queries? It will immediately also imply communication algorithm as well. And these are the main barriers that we need to overcome. One is for max flow. A good result would be a communication complexity upper bound. And for reachability, this is the conjecture I mentioned, which has a bunch of implications. All right. Also, pick your favorite problem and try to solve it in this model agnostic way. I think that's a nice way to go about solving problems. For example, you can look at disjoint forest. Directed cut is an exciting example because it's a submodular function minimization, but it's asymmetric submodular function minimization. Colorful spanning tree, arboricity, all these problems are very basic and we do not know much about. All right, there I will stop. Any questions, I'll be happy to take. Thanks.
Thank you very much. Do you have any questions? Any questions or mine? So about this conjecture, is it there's no evidence against it, that's why you believe in it, or is it an inherent reason you haven't told us about? Maybe I've missed it.
The former, essentially.
Right. So you're an optimist.
Well, try to prove lower bounds on it. Reachability lower bounds is one of the hardest thing to prove, essentially.
More questions? Anyone? No? All right, let's thank the speaker again.
Thanks.